Okay, let me see how far we can get on this topic then. Okay, we probably won't finish, we only have 15 minutes. Okay, but now the next leg of the class, we're going to turn back to more emphasis on algorithms again. Often, a lot of our problems will have some NP-hard sibling problem, but it'll be a little bit more, it'll look a little bit more like the first few weeks of class, but with a little slightly different points of emphasis. Okay, so we'll start in particular so it's going to be a little more, especially kind of combinatorial optimization and certain related themes. Yeah, and the first one we're going to do uh, is spanning trees. So let's first just do a motivation. All right, so this is actually, I think, the actual origin of the problem. So, you just discover electricity is the 1800s or something. I think it's 1800s. And your goal is to connect the town with the minimum amount of electrical wire. Okay, and imagine those yellow lines represent where you could put wire. And imagine the amount of wire is proportional to the length as drawn on the screen. Okay, all right. So my question to you is, which edges should I take? Yeah. Which one? Maybe that one? Seems like a smart idea. What else? Well, you have to tell me which one. Maybe like this. Like the length of the yellow line or something, which is roughly. Oh, the numbers are just naming the houses. A little ambiguous. Okay. All right, so now we've kind of connected all the houses. It makes a tree. The tree is sort of like minimally redundant. There's no redundancy, right? And at least looking at this, it's not obvious how to improve it. Certainly, it doesn't seem appealing to swap one of these edges with another. It looks at least locally optimal. Okay. Yeah, so some quick observations. There's no reason to have a cycle. Just a redundant connection. Everything is kind of a positive cost. Uh, it seemed very natural to take the shorter wires. You guys all gravitated to that. And the unused wire, so every wire I didn't use, the endpoints are still connected. Yeah. Although the path that connects the endpoints could be longer than that particular edge. Okay, good. So I'm going to introduce some terminology. So a circuit will be any walk that starts and ends at the same vertex. Oh, I know it's confusing because we just talked about circuits in a different way. I want to reserve the word cycle for when the vertices don't repeat because of all of our Hamiltonian cycle type discussion. So the circuit in graph language actually refers to this. Okay, apologies. In a forest can be defined as any set of edges with no circuit. It's also the same as not having a cycle. Okay. You can also say it's made up of trees. Or you could say a tree is a forest with only one connected component. Okay, I think you all kind of knew some of this terminology at least before. Okay. All right, here's another bit of terminology, spanning. Okay. I'll say a bunch of edges over here spans this particular edge if it already connects the endpoints of that edge. Okay, so in this picture, E is that blue edge, S is in red, and this spans E insofar as it already connects the endpoints of E. Yeah, like back in our picture of our houses, all the edges we didn't take should be spanned by the set of edges we did take. Okay, good. So we're going to look at two problems, not just one. Okay. One is how do we get a forest of maximum cardinality or weight? Okay. And the other is, how do I get a spanning set of minimum cardinality? So they're like packing, so forest, you're trying to take as much as possible, but not creating any circuits or cycles, any redundancy. And spanning is sort of a covering requirement, right? You want to make sure you're covering and connecting all the edges in the graph. So like all the edges is fine, but you want to get as small as possible. Okay. You want to get the largest forest possible. Uh, yeah, so this would be already be a maximum cardinality. You can't add, it's at least a maximal one, right? You can't add any edges and still have a forest at this point. Yeah, so that problem was trying to get the maximum. It's slightly different, but so the two problems we're going to consider is to get minimum cardinality, minimum number of edges in any spanning set. The other problem is how many edges can you take and still get a forest? A tree just means there's one connected component. A tree is a forest, but a forest may not be a tree. So here I have four components. 1, 2, 3, 4. That's one forest consisting of four subtrees, kind of four trees in it. If I kind of add edges to connect them together, then I'll get a tree. If I add this edge, it won't be a tree anymore. We'll have a cycle. Okay, so these are these two problems we're going to consider first. Okay, a maximum cardinality forest and a minimum cardinality spanning set of edges. We'll do weight afterwards. Yeah, it's not. The graph might not be connected. But we'll start with this. Let's say the graph is connected. Okay, so we're going to start with two things. So we're going to consider the problem jointly. Okay, so the first claim is that any forest has at most n minus 1 vertices. And the second claim is that, or any n minus 1 edges, sorry, is that any spanning set has at least n minus 1 edges. And we'll do maybe the first one first. So how can I argue that in a connected graph, or really any graph, there's at most n minus 1 in any forest? Yeah. Okay, so how do you argue this? Right. That's for planar graphs. Huh? Sum of degrees of what? Of the vertices, and well, there could be lots of edges in a graph. Yeah. I mean, that's what you want to say, but can we sharpen that? What do you mean there's... Okay, let me just do this an old-fashioned way. Okay. Um, I just want to get it down nice and clear. I don't think anyone doubts this is true. Just want to articulate it. Okay. So here's one way. We'll start with an empty forest. You add edges one at a time, right? So initially, when there's no edges, kind of how many connected components are there? n. And every time you add one edge, what happens to the number of connected components? Decreases by 1. Exactly 1. And how low can it go? Okay, good. So how many times can you add an edge before you run out of space? N minus 1. Okay, so I think we all believe this, but we just want to get it down cleanly, easy to verify, right? Sometimes the essence of a proof is not that you're proving something unbelievable. You're just trying to figure out how to cleanly explain in a verifiable way what you readily know. Okay, good. All right, and there's other ways I'm sure to do this. This is just one. Okay. All right, let's try to come up with, again, this claim should also be intuitive to you. But let's try to figure out one way to maybe get it down fully and rigorously, but cleanly. So the claim is that any spanning set of edges, so in a connected graph, has at least n minus 1 vertices. Yeah. Okay. Okay, so suppose I had a graph with n vertices. That would be the first sentence. Okay. What would be the second sentence? Yeah, but it's getting a little bit wishy-washy here. I don't disagree with the ultimate correctness, but we got to figure out how to explain what we mean. No, any spanning set of edges has to have at least n minus 1 edges in it. So it's a set of edges that spans all the edges in the graph. So you start with a graph G. Not necessarily. I mean, you're just told that G is connected and you have a spanning set of edges. We just want to show there must be at least n minus 1. Sure, but we just got to figure out how to state it. So the first sentence is you have a graph with n vertices. What's your second sentence? Yeah, we've established n equals 2. It holds for everything smaller than n. And I give you a graph with n vertices. What's your second sentence? You're doing induction the wrong way. You got to start from n and make it smaller. Yeah. Okay. Okay. But now when I split the graph, what if those two parts aren't connected? So this took as hypothesis that G is connected. So if you split the graph, it's not connected. Okay. But what if removing that vertex disconnects the graph? It's, yeah, but it could be in the middle of two sets of edges. How do you know there's always one that exists? Funny, right? Like, I'm not sure. It feels a little flimsy. Okay, how about this? Okay. Well, let's see where this goes. Okay, let S be any spanning set, right? So now there's only one connected component with respect to S. Okay. Uh, if you delete an edge, the number of connected components goes up by at most one. Yeah, you have a big connected blob, you delete an edge, you might have two connected blobs, but you won't have three connected blobs because you're only deleting one edge. Start with one connected component. Each time you remove an edge from your spanning set, it's no longer spanning after the first edge is gone, possibly. But number of connected components goes up by one. And how high can it go? N. So how many edges can you remove? N minus one. That's at least easy to read. Yeah? Okay. I'll try to make this next part quick. Okay. I'll try to get us out of here. So now suppose G has K connected components instead of one. Now I claim instead of N minus one, we have an N minus K. But why? Yeah, so we can just treat every connected component of the graph separately. 10 minus 1, 9 minus 1, 5 minus 1, and add them all up. If there's K components, you get K minus 1s. So that's not too exciting. Okay, so I think we can, well, I might need a couple of minutes. So let me say something. Okay, so a maximal forest is a forest where you can't add an edge and it still be a forest. Maximum forest is a forest with truly the maximum number of possible edges. Okay? Same with minimal spanning set and minimum spanning set. Okay, I want to make a small distinction here between maximal and maximum. Minimal, minimum. Okay, am I gonna be able to do this? Okay. Yeah, we're going to try to show that. Okay. So an algorithm that gets a maximal force is very easy. You just go through the edges. Can I add this edge? Maybe, maybe not. Can I add this edge? Maybe, maybe. When you get stuck, you have maximal. Same with minimal spanning set. I can keep removing edges as long as I retain the spanning property. But the question is, will this algorithm get you a maximum forest? And will it get you a minimum spanning set? Will this simple algorithm actually get you an optimum solution? And then also, how do we prove it? So a spanning set is it's going to be big and getting. Yeah. Okay. So let's see this. Okay. So here are two claims. If F is a maximal forest, then it's spanning. The other claim, if S is a minimal spanning set, you just can't remove an edge, then it's a forest. Okay. Why is that interesting? Well, because you know that any forest, size of a forest is less than equal to any size of a spanning set. That's what we showed. Size of F less than equal to N minus K, less than equal to size of S, right? So if you show that a forest is spanning, then it must be maximum. If you show that a spanning set is a forest, it must be minimum, right? And the key point is you have these problems that are actually two sides of the same coin. And you can use them to you can use these two different ideas to mutually certify optimality. Question is, how do we prove these things are correct? So this is a duality argument. Okay? It's only by taking into consideration the kind of forest and spanning jointly that we're going to try to be able to certify both. Okay, so we just have to prove this thing. I know I'm over time. Okay, but I think we can do it. It's actually not so bad, and I think you guys can fill this in. The claim, if a forest is maximal, then it's spanning. That means that any edge is already connected by your forest. Why? Yeah. Yeah, so if you have an edge that's like not spanning, then what can you do? Huh? You can add it to your forest. It doesn't induce a cycle because it's not spanning. So it wouldn't have been maximal. You have a contradiction. Okay. All right, how about this one? If S is a minimal spanning set, then it must be a forest. This is really the last slide. There might be some like wrap up, but yeah. So last point. I'm very sorry. If S is a minimal spanning set, then it's a forest. Yeah. Yeah, so or if it's not a forest, then there's a cycle. So not forest, then you have some kind of cycle, right? And if you delete this edge here, you still have this connection. So you'll be okay. It'll still repair everything in the graph. I'm going a little bit quick because I'm over time. Okay? So that's really the point. Okay? It's by considering these two problems jointly, these two opposite problems, but they kind of meet, they mutually certify each other. And this algorithm that seems like everyone kind of knew, oh, the greedy algorithm should work, is probably some intuition you all had, but they actually work for both problems for the same reason at the same time, so to speak. Yeah. So that's our first example of a duality argument being used to prove optimality. So we'll do more sophisticated problems, including the weighted version, next class. But these are going to be problems in combinatorial optimization that often have this primal and dual aspect. Okay. All right. Sorry to go over. Enjoy the weekend. All right. So we started this last time, so let's get caught up. So we're talking about spanning trees. A motivating problem is something, a historically motivating problem was you're actually trying to lay a minimum amount of electrical wire to connect houses, like roughly when they kind of first discover electricity. Um, so this is actually a bit of an exercise in terminology, and if you get the right definitions and concepts down, actually the subsequent proofs aren't so bad. But I'll quickly go over them again. A circuit is any walk that starts and ends at the same vertex. It could be a cycle or it could repeat vertices in the middle. A forest is a set of edges with no circuits. So forests are made up of trees. Or a tree is a forest, but there's only one connected component. Okay? And a big word in this lecture is spanning. Okay, so spanning means you connect the endpoints of an edge. So a set of edges S spans another edge E if the endpoints of E are connected by S. Okay? It's actually not so different than spanning in linear algebra. But we were looking at via something called metroids. But we're looking at two problems, okay, that turn out to be somewhat related. Okay. One is, what is the largest possible force you can get? So let's say the edges are unweighted. So you're trying to take a lot of edges, but you can't create any cycles or circuits. How many can you take? And the other problem is, how do you get the minimum set of spanning, this minimum spanning set of edges? So you want to make sure that everything's connected, but otherwise using as few edges as possible. Okay, so when you're trying to take as much as possible, subject to sort of an implicit packing constraint, oh, you took too much, there's a cycle. The other is you're trying to take as few as possible, subject to like an implicit covering constraint, oh, you took away too many, those aren't connected anymore. Yes. So, okay, so and then we started doing uh, stuff like this. Um, so one was the argument that, oh, in a connected graph, any force has at most n minus one edges. Okay, which I think everyone believes, but it was a little bit tricky to actually get it down cleanly. One way to prove this is to start with an empty force and just count the number of connected components in the graph. First, there's no edges, so you have n connected components. All the vertices are on their own. One by one, you add an edge, and each time you connect two different connected components, right? Because you're not creating a cycle. So the number of connected components goes down by one. You start at n, you end at one. You can only add n minus one edges. Okay? And we had the other statement was that any spanning set of edges must have at least n minus one edges. And we need another kind of similar counting argument. Once you set it up, it follows in a straightforward fashion. Um, so if you start with a spanning set of edges, then everything must be connected. So there's one connected component induced by your set of edges. Now remove one edge at a time. You know, it's possible that edge is like redundant and nothing changes, or it might create two connected components out of one. The number of connected components may go up by at most one. You won't create three new connected components. Okay, so you start at one connected component, you get down to n, and you must have removed at least n minus one edges from S. Okay, so S has at least n minus one edges. No induction, just counting, and just careful kind of understanding of the definitions. Okay, so you want to do this for K components instead of just a connected graph, no problem. You just apply the argument to each one. That n minus one, the minus one shows up K times, and that's how you get n minus K. Okay, good. So the second part we discussed was trying to understand the difference between maximal and maximum, and minimal and minimum, right? Local versus global kind of optimums. Okay, so maximal forest means I have a forest and I can't add any more without creating a cycle, add any more edges. Maximum means I truly have the largest number of edges possible in a forest. Maximum always is maximal, but not necessarily vice versa. Similar for minimal and minimum. A minimal spanning set is a set of edges where I can't remove anymore. And minimum is truly attaining the minimum number of edges over any spanning set. Minimum is always minimal, but minimal may not be minimum. Of course, we covered this last time. So what we showed last time, actually, we're going to show that maximal is maximum and minimal is minimum, but in sort of a curious way. We showed directly that a maximal forest, I can't add any more edges, is necessarily a spanning set of edges. And we showed a minimal set of spanning edges, a minimal spanning set, is a forest. There's no cycles in it. And because we already showed that any forest has cardinality less than or equal to any spanning set, once I showed my forest is a spanning set, I know I got the optimum. I got the maximum. And as soon as I know my spanning set is a forest, then I know it's the minimum. Okay? So the beauty of this argument and sort of the power is the way that we look at these two opposite things that mutually certify each other to be optimum. Right? Which is a different style of argument than we've had in this class. It's a duality argument. There's some kind of dual, right? A is less than or equal to B, but if I can get A to meet B, then it's tight. Okay? Yeah, I think the argument was fairly straightforward. If F is maximal, but if it wasn't spanning, that edge that's not being spanned, you should be able to add it and increase the size of your forest. And then on the other side, if you had a set of edges S and it wasn't a forest, then there must be a cycle or a circuit, and you should be able to remove some edge without creating any disconnections, right? Because the rest of the cycle will still connect those endpoints. Right, so anything that's not a force cannot be a minimal spanning set because you should be able to remove an edge from a cycle. Okay, but in that way, we've shown that maximal is maximum for force, minimal is minimum for spanning, and then that tells you that a simple greedy algorithm would have worked. right? Because it's very easy to get a maximal force. I just keep adding edges until I can't. And it'll tell you that then you're also done. You got the true answer, right? So this is a rare situation where greedy works, but it required a lot of care to justify that greedy works. Same with minimal spanning set. Oh, you could just start with all the edges and just keep removing them until you can't, and then you're done. That's pretty easy to implement. But because of the care we put into the analysis and understanding the structures at play, this minimal solution we get is actually the optimal one. Okay? So good, good. That also tells you that there's n minus one edges in a spanning tree. You kind of knew this. Okay, good. So now our next thing is to think about weights. Okay, so that was just cardinality. Now we're going to incorporate weights. It's going to get a little more nuanced, but not so bad. And for simplicity, I just assume all the edge weights are distinct. Okay, it's not so hard to modify arguments for when they're not distinct. Or if you're really lazy, you can imagine adjusting the weights slightly in a pre-processing step. Okay? So, like, you can just break ties alphabetically based on some alphabetical naming of the edges, and then that'll get you effectively distinct edges. All right, so in fact, we're going to come up with an algorithm, but what I'm going to try to do is I'm going to try to present like 5 algorithms at once, or I don't know, some number of 3 algorithms at once. But basically, we're just going to try to understand the structure, and then we'll see there's many different algorithmic choices you can make to implement it. They have different trade-offs, some faster, some more parallelizable, whatever. Okay, but we're going to spend time just understanding the structure of the problem, and everything else will fall out. So, okay, so I think the key definition for us, at least the way I'm presenting it, is I'll have something called a good edge. Okay. Oh, I should establish something. We are trying to get the minimum weight spanning tree. Okay. So, I could have done maximum weight, but the notes are set up for minimum weight. Okay. All right. So good. All right. So good edges. So I'm going to say that an edge E, which has some weight, okay, I'm going to say it's good if for any other set of edges that spans it, so there's a bunch of edges out there, it creates some circuit, it connects the endpoints, okay? It should have at least one edge, okay, where that edge has weight bigger than E, okay? So E is good if it like never looks like the heaviest edge on any cycle, is I think an equivalent way to express this. Okay? So we're just going to keep that definition in mind. All right, so now here's a claim. Okay, so the second one is just saying E is good written out. Okay, so the point one is okay. Let pick a particular edge E. I'm going to say point one is saying that E is contained in every minimum weight spanning tree. Point two is saying E is good. So put them together. It says that E is good if and only if E is contained in every minimum weight spanning tree. Okay, so that's the claim. The claim is that E is good if and only if E is in every single minimum weight spanning tree. Yeah? And that would be very useful because then we could try to make an algorithm that looks for good edges. All right, so now the onus is on you guys. All right, so let's try to prove this. Okay? So suppose every minimum weight spanning tree contains E. Okay? Uh, the claim is that E is good. So let's say that every minimum weight spanning tree, and really just let's say there's a minimum weight spanning tree that contains E. Okay. Now we want to show that E must be good. Any ideas? Okay, so let's go through slowly. So let's say that this is the MST, the minimum weight spanning tree, and there's some edge E that's in it. Okay, and then you say then you suggested what if E wasn't good? Okay, so if E wasn't good, then what must that mean by definition? Yeah, I can find some kind of set of edges that spans E. It might include part of the MST. It might include other stuff, right? Where by definition, the weight of E must be bigger than the weight of every edge uh, on this cycle. Okay. I should maybe draw this a little better so it looks, oh, oops, looks more like, all right, so maybe it interacts with the tree like this. Uh, if I were to draw nodes, maybe it would be like this, something like this. Those are the local nodes. Okay. All right. So on that red cycle or the red path that spans E, the weight of every edge on that path is bigger than E. So in that picture, what can we do? So if we remove E, that'll take my spanning tree and divide it into two parts, right? We have one side over here, and well, that wasn't a great picture. I guess one side of the tree is kind of over here, and the other side of the tree is, over here or something, right? So you split your tree into two components, and that red path that spans E, it starts on one side, it ends on the other. Starts on one side of a river, ends up on the other side of the river. At some point, it must cross the river, right? So there must be some edge going from one side of the tree to the other. And in this particular picture, um, that would be this one up, up here. Okay. And we're told that the weight of this edge must be bigger than the weight of E, less than the weight of E. I was only off by a bit. And so if I removed E and added this other edge, the weight of the whole spanning tree would go down. That shouldn't happen. And that's our contradiction. Okay, good. Okay, so that's one direction. Okay, now let's go the other way. Suppose E is good. Then every minimum weight spanning tree must contain E. Yeah. Yes. Well, you don't know that every minimum weight spanning tree contains E. You want to show that every minimum weight spanning tree contains E. So like you might have like this purple might be a minimum weight spanning tree, and then suppose by contradiction it didn't contain E. E was this red edge. I don't know why I didn't choose blue to be consistent, just to keep you on your toes. Okay. So So E is good, but apparently it's not in this minimum weight spanning tree. So ideally we should find a contradiction, yeah. Yeah, so the tree being spanning must span E, which means there must be some path connecting the endpoints of E, right? And since E is good, there must be some edge along this path with bigger weight. So maybe it's this one. This is F, and the weight of F is bigger than the weight of E. Okay? And if I delete F, then I'm going to end up with the spanning tree divided into two components. Okay? And then the rest of the path, we have some path that's kind of going through the trees and then taking E and then connecting back, right? So E is going across to two components. So adding E will repair the tree and get me back. Okay. So that's it. So if E is good, then if I compare it to any tree, then we're going to get some path in the tree connecting its endpoints. And we should be able to improve along some edge. Okay, good. So that establishes some kind of generic algorithm. Okay, where I start with an empty spanning tree, and I just repeatedly keep trying to add good edges. Okay. Now there's a couple issues. What are some issues? Or what parts of this algorithm are kind of unspecified? Yeah. Yeah, we need, yeah. How are we going to characterize and find good edges? Okay. And like, what if you run out of good edges? Like, and you're just going to give up, right? So some things we haven't quite filled in. Okay. Does anyone have any ideas for trying to get a good edge and why? Yeah. The smallest weight edge in the entire graph is definitely a good edge. Okay. So we can do that first. Let's see. Is that our, um, okay, good. Those are the two questions. We haven't given away anything yet. Let's see. Uh, okay, that's an idea. So minimum weight edge is definitely good. Let's say our algorithm takes that first. And what? I think implicitly, yeah, but let's try to figure out how to make this clear. Well, okay, what's a natural guess after the first minimum weight edge? Like, what's the first thing? Maybe the second smallest weight edge is at least, I'm imagining that's in everyone's head, right? Unless somehow it's already spanned by the first edge. I guess in our case, that can only happen if it's a parallel edge, which probably wouldn't happen. I mean, you can remove those. So probably the second edge is okay. Maybe they're connected, maybe they're floating apart, in which case it's really safe. And then what's a reasonable next guess? Third. But what's the one liability? So if your first two edges like look like this, and a third connected my pinkies, then actually that would be bad. Yeah, so you want to find edges that aren't yet blank by the edges we've already taken. Spanned at some level, right? So that kind of thinking, maybe we can try to justify that. Okay, so I guess here's a general lemma then. Um, okay. So you guys already noted that the minimum weight edge is always safe. And probably the second minimum weight edge is always safe. And probably the third minimum weight edge, but you can identify the one case where it isn't. So you have some sense of the small. So this is a little bit more general. It says pick any set of edges H, which could have been the first two edges we've taken or something, right? And they span some edges. Okay. Look at the remaining unspanned edges. The claim is that the minimum weight unspanned edge relative to whatever set H is always going to be good. Okay, so H is just some amorphous blob, right? So H is just a bunch of edges. They might be big, they might be small. We're not saying anything about it. Didn't want to erase. Okay, so you have some arbitrary edges H, and then you have some edge E that's the minimum weight among all edges that aren't spanned by H. We want to argue that E must be good. And then that would be very convenient algorithmically because we can just find sets H that justify our next choice, right? So I think the why this might be useful hopefully is clear from because it would immediately justify our greedy algorithm. Keep taking the next unspanned edge of minimum weight, right? So if we can just get this lemma, then we're really in the clear. Ideas? Uh, does that just follow from definition of good? I mean, it's going to follow from the definition of good. Just, I don't know. Maybe I'll let you guys fill in the just part. Yeah. Wait, spans H? Well, yeah, so H is some set of edges, and E is not spanned by H. So H doesn't connect the endpoints of E. Okay. But E is the smallest weight edge that's not spanned by H. So you want to say that E is good, right? So, you might do something like, well, let's take any other set of edges that spans E. We want to show that there's at least one edge of weight bigger than E on this path. Yeah. Yeah. Among. Well, some of these edges may be in H. Yeah. Yeah. I think that's the same idea, but let's just try to draw it out and try to figure out how to. Because if you just wrote on the paper, can't we just contract the vertex and imagine? I think that's sort of like sweeping it under the rug. And I just want to draw out this intuition we have in mind. Right, so blue is some other set of edges that does span E. I want to argue there's at least one blue edge that's bigger. Yeah. There must be at least one of these edges that aren't in H. Otherwise, H would span E. Okay. So yeah. Yeah, so that edge that's not in H, uh, and also is not spanned by H, right? Um, it must have weight bigger than E because E was the minimum weight edge not spanned by H. That's it. Okay, good. Good. Now, now we can start just vomiting algorithms. Okay, so the greedy algorithm. Let's take the minimum weight edge. Okay. Now let's take the second minimum weight edge. Okay. Now let's take the next minimum weight edge that's not spanned by the first two I've taken. Okay, let's take the next minimum weight edge that's not spanned by the first three I've taken. Okay, so this might be obvious, but that fifth, what are the sets H that justify our choices? So when I take that fifth edge and I want to apply the lemma to say, oh, that edge was safe, what's my set H that certifies it? The first four edges. Yeah, the 10th edge is justified by being the minimum weight edge that's not spanned by the first nine. So it's a direct kind of iterating this lemma again and again. Okay? And that's the whole, yeah. Ah, yeah. So another implication then is that you're actually going to fill up the tree with good edges. What does that also say about the minimum weight spanning tree when the edge weights are distinct? Because we said that every minimum weight spanning tree contains every good edge, right? And you just filled up, yeah. There's n minus one good edges, and the minimum weight spanning tree is unique. So when edge weights are distinct, the minimum weight spanning tree is actually unique, and it's all filled up with these quote unquote good edges. Good is not really a technical term, like I made it up, but okay. If there's ties, then you can swap one out for the other. It's not hard to adjust this whole discussion for when there are tied weights. It just gets like we just need an extra sentence every time. It's annoying. Okay. Okay. Well, actually, maybe I don't have to. Maybe you guys can try to guess more algorithms. So the greedy algorithm will work. But now that you know kind of how much flexibility you have, any ideas, other ideas for an algorithm? Ah, yeah, that algorithm will work. That's an exercise. The suggestion is, can you start out with all the weights and then just keep removing the biggest weight edge that is? It kind of doesn't break your spanning property, right? Um, yeah, I'm trying to figure out, can that be directly addressed by our beloved lemma? Like, my beloved, I don't know if you guys are as fond of it as I am. Um, yeah, it might take a little. I think if you, so you want to show that this edge you remove is not good. Okay, what does the contrapositive look like? Or yeah, or maybe we can show that we never remove good edges. Yeah, so if I remove the maximum weight edge left, but it's not breaking the spanning property, so the remaining edges already still span it, and it's bigger than everything. So that already gives you a set that proves it's not good. Okay, good. Yeah. Yeah, contrapositives are tough to do in front of a crowd because you flip everything. Um, but yeah, okay, you can show that it's never a good edge that you remove because the remaining set of edges is already still connecting everything, and it was okay. Okay, good. So that'll work. All right, other ideas for algorithms. Yeah. Uh, oh, okay. So if you look at any, if I split the graph into two parts, to the vertex set into two parts, and I find a minimum weight edge going across the two parts, is that edge always good? And what would be the set H to justify it? I could take all the edges inside one half and inside the other half, and those will be collectively H. And the edges that aren't spanned are the edges going across my two parts. And you got the minimum weight one. So you can keep splitting things in half and adding edges. The minimum weight edge across the cut. Yeah, that'll work. That will work. Any more ideas? There's a lot of things that could work. So this is like, in fact, can anyone think of an algorithm that wouldn't work? Might be trickier. You probably could, I'm sure. Yeah. Well, that's what this greedy algorithm is basically doing. You can sort them ahead of time if you wanted. I should mention these all have names. I think this is called Kruskal's algorithm. I don't remember names, but yeah, somewhere. Yeah, there's going to be more. Yeah, you guys have all vaguely heard these names. All right, here's another one. Okay. So initially, so every vertex, a vertex can just choose its minimum weight edge incident to it. Okay, I claim that for a vertex, the minimum weight edge is going to be a good edge. But why? What would be the set H? Yeah, it is the edges that don't involve this vertex that connects everything else. So the only remaining unspanned edges are the edges that are going to your fixed vertex. Okay. So that allows for the following kind of parallel algorithm. Each iteration, every vertex chooses its minimum weight edge in parallel. And you can imagine contracting the graph along all the selected edges. Or if you want, you don't have to contract it literally, but after one round, you have some connected components based on the edges that got chosen in round one. Now, every connected component chooses its minimum weight edge, leaving the component. Okay. And then that'll add some more edges. And you repeat and you repeat and you repeat and you repeat. Contracting the edges, right? And then each connected component looks like one vertex is the same as in the other version, kind of acting as if the connected component were a vertex. Okay, so that's kind of nice because you can choose a lot of edges in one round in parallel. There's no conflicts between the decisions, especially when the edge weights are distinct. Okay. Good. We'll get to running time in a moment. All right, so that one's called Borufka's algorithm. It's not the one you had in mind. Any other ideas for an algorithm? So you can do one that's maybe sort of like locally growing. So I started a vertex and I choose the smallest weight edge. Now I have those two vertices. And I want to keep exploring. So maybe I find the next edge incident to one of these two vertices, but not going between them. Okay. So that's maybe like a search algorithm. So the idea is you kind of like, you start with one vertex and you add one edge at a time, but you kind of maintain connectivity. So you kind of gradually grow, blob, kind of looks like Dijkstra's algorithm. So you keep finding that next edge that gets you to a new vertex, but connected to the ones you've already connected. Okay. Was Dijkstra Prim's PhD advice? I don't know, but you all have your laptops in front of you, so okay. Some were polite enough to close them. Okay. All right. So we have three algorithms. Uh, can you even see that from here? That's the greedy algorithm, the parallel algorithm, and the search algorithm. And so now we're going to analyze the running times and just understand their differences. Okay. So let's look at the greedy algorithm. So the first step you might do is sort all the edges. That'll take, m log n time. There's m edges, you sort them. Uh, and now what's the bottleneck? Yeah, so you have an edge and you want to see if you can add it. In which case you need to know if the endpoints are already connected. Okay. So to that end, you need did you guys already learn this? Okay, so this disjoint union data structure. So the data structure's interface is like this. You have a bunch of elements originally, and you're allowed to kind of glue them together into sets. So I can, oh, these two elements are in the same set. These two existing sets are now in the same set. You can just take the unions of things, and then you can ask, are they in the same set? So how do we apply that to our graph problem? Yeah, what are the sets? Yeah, the connected components of the edges we take so far. And whenever we add an edge, we're taking the union of the two different components. So did you guys do the full analysis? Okay. Okay, yeah, so you can do this does work exceptionally well. You could do a full lecture on like slightly different variations and gradually building up to this. Like Jeff has a very nice Jeff's notes where I sometimes refer to problems. He has a very nice section on this. We could do it if you want at the end, but yeah. But it's a it's just a phenomenal thing that I think Tarjan got the running time down to this inverse Ackermann function, which none of us had ever heard of before it showed up in this data structure. Well, probably some had, but at least that was my first exposure. Not that I was alive back then. Um, okay, so in case you can't read it, uh, yeah, you do m plus n alpha n time. Good. Like it's not really a bottleneck here because you have to sort the edges in m log n time. So actually a relatively modest disjoint union taking log n time per operation would have been just fine. Okay, how about the parallel algorithm? So in the first iteration, everyone chooses its minimum weight edge, every vertex. How long does that one pass take? How long does it take to figure out for every vertex its smallest weight edge incident to it? Yeah, m total. So you don't even have to sort, right? If I'm just looking through a list and picking out the smallest, you don't have to sort anything. So it'll take m time for one pass. Then I contract everything. Okay. But then I have to also relabel the edges based on the new names of the vertices. But that's not so bad. I start at vertex 1, I do BFS or DFS, and I label everyone, and then I go and update the edge labels. Same as 2, 3, 4. So that takes m time to relabel everything. So the contract relabel takes m time. So the question is, how many rounds of this algorithm do we have? Sure, at most n minus 1, because we should be getting rid of at least one vertex, right? Contracting one, but we're doing a lot more work than that. So everyone chooses an edge, right? So by the time I take those edges and I contract them, how many edges are left? At most what? N over 2. Because every vertex in the new graph had at least two vertices from the original graph. Maybe more if the long chain. So it's log n rounds. And then this algorithm is very simple. It's completely parallelizable. You don't have to sort. So this is actually one that does very well in practice. Parallel people love this algorithm. Okay. How about the search algorithm? So here, I guess it will be helpful to bring back our old friend, the Fibonacci heap from Dijkstra's algorithm. Okay. So that means you could insert it and decrease in like constant time, but removing the min from the heap takes logarithmic time. Okay, amortized time. Oh, I shouldn't give that away. Okay, so okay, yeah. So with this data structure, so that means, I can keep trying to remove the minimum weight edge that's not yet spanned. All right. How long would it take? Yeah, m plus n log n. It is correctly. Yeah, but how do we actually implement it? It's a little tricky. Yeah. Okay. So this idea is to put all the edges that you could take into the heap. Now, when you remove min, you might get an edge that's spanned by your tree. And then you would have paid log n time, but you wouldn't have added an edge to your tree. So that gives you m log n. But what you guys have in mind is m plus n log n. So a slightly different implementation. So what do we insert in the heap? Remember, you can decrease priorities and stuff. Okay, so you have some tree, and then you have all these other vertices that you haven't visited yet. Okay? And then some of these vertices have edges that you could take, meant to be drawn in these dashed lines, right? So in the heap, we're going to put in every vertex that you haven't visited yet. Initially, all the vertices, except for maybe the starting one. And then their priorities be the minimum weight edge to that vertex from one of the vertices you've already seen. So you're really getting what's the next kind of closest vertex in a slightly different sense of the word closest than Dijkstra. It's just measuring the weight of the smallest edge. Okay. So that means when you take an edge, like when you take this wedge here and you add this vertex, then you may update the priorities based on the edges incident to that new edge or new vertex. Okay. And in this way, now you're only removing the min every time you add a vertex to your spanning tree. There's only n vertices, so you get m plus n log n. Good. All right, so those are the three running times. And so n plus n log n is probably theoretically the fastest. Although my impression is that Borufkas might be favored in practice. All right, good. I think because of the parallel aspects. Yeah. Okay, good. All right, so much for that. Any questions about spanning trees? Yeah. Yeah, so Kruskal, you need to sort the edges to get m log n. Oh, well, how big is m? N squared and log of n squared is n log of n. Yeah, good. Other questions?